Hello, my name is Arnav Ganguly,
My name is Neil.
and today we will be talking about our project Equilibrium Zen-centric Calculus. So, a short story about our project is that in the beginning of the year, we were filled with anxiety because there was a tide of expectations against us. But as the month flowed on and we finally faced the time of the AP exams, the turbulent waters began to still, and we began to find our rhythm emerging on the other side in a state of tranquil equilibrium, with us being the two koi fish finally circling one another in a perfect, harmonious balance of yin and yang. So this was our initial draft of our board. So what we had is the two cross sections over here representing the two fish, and then there was a acrylic sheet which we shaped in the form of a watery shape using a heat gun, and also LED lights around the border in order to have a watery effect. So these were the regions that we had. So as you can see, the blue and the green, it's a half ellipsis with cross sections perpendicular to the y-axis. So this is what our project was. And then we used parametric equations in this sort of format.
All right, so our parametric equations are F1, F2, G1, and G2. Since we didn't want to calculate the value of two equivalent fish, we just chose one. So let's focus on F. This is the parametric equation, and the part that is determined by the H constant is the spine of the fish, and the W of T over pi is the thickness of the fish. So if we add and subtract the thickness, we can get a full silhouette of the fish. So for our calculations, what we did was we took the x1 and x2 values, which represent the outside spine and the inside spine, and we subtracted them from one another to get the width of the fish, so we can do cross sections dy. A problem that we came through during this project was that we have to subtract a function from its own value. So that was a challenge that we had to face in this project, and how we got around that was we separated the function at around x equals 1.5, and what we did was we took the minimum value and we subtracted it from the maximum to get the full thickness of the values that are constrained by both values of x. And then we added this to the full domain of the x, and then we took the value, like the y value at each point for x1 and x2, and x1 represents the outside area of the spine, and x1 or x2 represents the yellow part. And we took x1 minus x2 to find the width of the fish, and then we took the volume of each subsection by getting a formula for um, for this cross section. So this is a half ellipse, and it precisely follows the silhouette of a koi fish, which isn't just a semicircle, it's more of an elongated fish. And the way we did the formula for the width is we took the area of the ellipse in terms of the width, and then we plugged in each specific width that we calculated with x1 and x2, and then we dragged it down so that it would give us each cross-sectional volume for the respective slice. To calculate the thickness of the slice, we took the total height of the fish figure, and then we divided it by the total cross sections that we counted. We made sure to include the same amount of cross sections for both fish because we wanted those values to be equal to each other. As you can see here, these are all the values of our cross sections, and we added them up to get the total estimated volume for one fish. Since the function was concave down, the midpoint Riemann sums ended up being an underestimation compared to the actual volume, which is calculated by the definite integral using the formula of volume. And the definite integral and the actual value of our cross section is equal to 38.24. Multiplying this by 2, we get 76.48, which is the total volume of both fish. This is an underestimation, as you can see here, because the estimation we got from the Riemann sum was 36.1. These are all of our different transformations that we used, and these are our parametric t values from 0 all the way down to pi. All right, now moving to part 2 of our project. We skipped over part 2 earlier. This is our full project that we created using these two cross sections. We curled these two cross sections around each other, just as described in the cross section. If we take both of these fish and we make them visible again, these are the two G1 and G2 equations that mirror the F1 and F2. And filling in these equations, you can see the bounded area that represents the project. Then, just to reassert that yin and yang, we took a kokuhaku koi fish color that represents the light and a utsumono koi fish that represents the darkness, and then we integrated that into the title and color of our fish. Thank you, and this is Equilibrium Zencentric Calculus from Neil
And Arnav.